Hey there, this is Mitchell with a video on acceleration. Acceleration is a change in velocity over a certain period. Now you probably see that we have an acceleration formula here, which kind of looks a little bit different from most of our other formulas. So let's talk about what these particular things mean. We have acceleration. This is final velocity. I'll go with a darker color. This is final velocity. This is initial velocity, and this is the amount of time it took to have the change of velocity. So say you have a Yoshi over here, and Yoshi accelerates. It accelerates from going a particular meters per second to a faster meters per second. You take the faster meters per second and put here, subtract the initial meters per second. So this will end up being a positive number if you have a true acceleration where you're going from a slower to a faster. Now this can end up, I don't know what I did there, but this can end up being a negative number, and you might can see how if Yoshi here decelerates. Let's say Yoshi is going at a 30 meters per second and then he goes down to 20 meters per second. Then the final is 20 and the initial is 30. So you can see how that could be a negative number, and all that means is Yoshi is decelerating, not accelerating. Accelerating is going to be going from slower to faster. Decelerating is going to be from faster to slower. So you will often hear final velocity minus initial velocity called change in velocity. And if you see this delta symbol here, that's what that stands for, change in velocity. And sometimes you see the formula as acceleration equals change of velocity over time. And we will do problems in a moment on that. So a change of velocity, if you were to have miles per hour, I was tempted here to say Yoshi was going 30 miles per hour, but if you do have something like 30 miles per hour or anything in miles per hour, know that you're going to need to change that to meters per second. Yes, the change in velocity is going to be in meters per second. Now the time, you can probably imagine what the time would be. The time would be in something called seconds, as you know what that is. So that's meters per second, which means, shortened, it's going to be meters per second squared. So when you're looking to find acceleration, it is going to be in meters per second squared. A force can act upon an object's velocity, causing it to accelerate or decelerate. Now that sounds pretty simple, but we probably need to define force, and you see we have some kinds of forces under here. Looking in my notes here. Multiple forces work upon an object. For example, Yoshi's moving car is not only subject to the force of his little motor here, he is subject to other forces that determine how fast, if he goes any speed at all. You may have some kind of wind that is a force that might come against him. You have the friction of the tires, which is a force that would hold him back. And you even have gravity here, which is a force that is keeping him on the ground. So there are lots of different forces that can affect any moving object. It might affect its acceleration, it might affect its deceleration. Now, if you have zero force, and they often call this net force, but if you have zero force, that means all the forces are canceling out. Now what that means is, if you have zero force, you have a balanced force, and the object is not moving. If Yoshi here is not moving, he still has forces coming against him, wind, gravity. It's just that the strength of the motor couldn't overcome it, or he's just not choosing to use the strength of the motor. Maybe this is a better example. Here you have three people pulling this way, and you have three people pulling this way. Now, obviously, there are forces going on. Each of these three people here are making a force to try to pull it this way, just like these three are. But there is a chance that there may be no movement. If they both have an equal amount of force being pulled upon with them, along with all other forces like wind and friction and gravity, no movement will take place. So whenever you have a balanced force, balanced forces, you have no movement. And of course, you can imagine what's happening whenever you have unbalanced forces. You have movement. With all movement you're going to have, you're going to have several forces to try to resist it and to promote it, just like we were saying with Yoshi up here. The friction, the gravity, the wind, all the force of the motor, all those forces are going to combine to either let him move or not move. And if it's if they are unbalanced forces, then you have a force that is winning out. And probably in this case, it's going to be the motor that is going to overcome any of that. Now, we mentioned friction. Friction is the resistance of an object to move. Resistance of an object to move. So you have the tires, resistance of object to move. You have the tires on his vehicle. The tires have friction. Whatever is touching the ground has friction. Of course, that is a force that slows it down. If you were to take a marble and just roll it down the hall, eventually the marble will stop as a result of the friction. Now, we do have another kind of friction, and that friction is air resistance. Air resistance is sometimes called drag. Let's take a look at air resistance here. Air resistance is a form of friction. It is the interaction between the air and the moving object. As a car accelerates, like this car right here, the air resistance is a force that can help slow it down. This car will not go as fast because it is going against the air. Now, notice I put two different cars here. This car has a lot of surface area. Notice the windshield is standing up much straighter than this windshield here, the sleek, nice sports car. And that's going to affect air resistance. The greater the surface area, the greater the air resistance. So if you have a boxy car like you have right up here, it's going to have greater air resistance as it does the sports car, as long as it's going of an equal speed. Because if you have more speed, you have more air resistance also. And it only makes sense. If this car is going 50 miles per hour, it will have less air resistance than if it's going 100 miles per hour. So the larger the speed and the larger the surface area, the more air resistance you are going to have. Now, I had up here the word gravity, and I have not talked about gravity yet, but we do have some stuff to talk about gravity. Now, when we think of gravity, we often think of the force that keeps us on Earth, and you can also think of like our Earth is in rotation or revolution around the sun because of the gravitational pull. But there's kind of a science behind this gravity and the two factors that affect gravity. The two factors that affect gravity are going to be the mass of the two objects. For example, the sun is a very large object, and the distance between them. Now, before I start talking about these big distances and big masses, every object has some kind of gravitational force behind it, we think. It's just that here on Earth, we don't really kind of feel that very much outside of the gravitational pull of our own Earth. So, mass and distance are the two things that affect gravity. The amount of gravitational pull depends upon these two things. So if you have one object in space and another object in space. Let's make one of these objects bigger, kind of recreating something that the other object would revolve around. If you have the mass of them is going to determine how much gravitational pull they have. For example, if you have another object out here which has a smaller mass than this will end up revolving around the larger object. It'll be in orbit, you might say. But notice what will happen. Let me erase some stuff here. Notice what will happen if you have a change of distance. Now, if you have this object here that, say you put it double the distance away that it was. Now, I know we can't exactly go do that, but say we put it double the distance, you might expect for it to decrease the gravitational pull by half of this larger object, but it actually does more than that. It decreases the gravitational pull to 1/4 of what it once was. So get this, instead of being half of what it once was here, it's 1/4 of what it once was. So it kind of decreases logarithmically, I guess you might say. Say it were to be triple the distance. If you were to triple the distance instead of double the distance, I don't know that this is a true triple the distance here, but it would be 1/9 of the gravitational pull that it previously had. So you really have, because distance really does mean a lot as far as gravity goes. And one thing you can see is our moon. Our moon is very, very close to our sun. And because it's very close, it has so much influence on the tides. Now, the sun is huge, but the sun is so much farther away than the moon is, it just doesn't have much of the same distance that the tides do. Okay, let's find some acceleration here. A runner increases his velocity from 1.5 meters per second to 3 meters per second in the last 30 seconds of a race. So, acceleration equals final velocity minus initial velocity over time. So the final velocity looks like it is 3 meters per second minus the initial velocity, which looks like 1.5 over the seconds. The time is going to be 30. Hey, I think this will be a pretty straightforward one. 3 minus 1.5 is 1.5 over 30. So let's see what that calculates out to be. 1.5 divided by 30 equals, looks like 0.05. And let's see, what kind of unit would that be? 0.05 meters per second square. That's right. Take a look down here. A runner gets tired and decreases his velocity. So we're going to have some deceleration here, but we still use the same formula. It's just going to be negative. So we have a final velocity minus initial velocity over time. So let's see what we have. We have final velocity is 1. 1 minus the initial velocity, which is 1.5. So you're going to have negative 0.5 up at the top here. And the bottom is going to be 60 seconds. So there's going to be negative 0.5 over 60, which I happen to know that one. Well, I better make sure. Let's go with 0.5 divided by 60 equals, that'd be 0.0083. So the answer is 0.0083. And don't forget the negative, because it's deceleration. That's a bad looking zero there. But it's going to end up being in meters per second squared. Well, there are some calculations for acceleration, and I hope you've learned a little bit about acceleration, forces, and friction and gravity.